Okay. Let's look at some of the things we've been talking about with linear regression. So we brought up kind of the basics of linear regression. We even created an equation for it last time, if you'll recall. We created the linear regression equation for this specific data over here. We made a prediction as to what the exam score would be if you studied 6 hours on average. We're not going to get too in depth on residuals. What we'll do though is I'll go ahead and repeat this for you real quick, just so we have it available. And for me, I'm literally just Googlifying linear regression calculator. And I'm going to enter it in. I'll show you what I enter in just a moment. And so here we go. This is what's getting added in. Yes, I watch Minecraft. I play Minecraft. I'm a 31-year-old man, and I'm proud to say I play Minecraft. Oh, you must have played that when you were a kid. No, it did not come out when I was a kid. I was a 21-year-old man when it came out. So you're just gonna have to, let it be. So these were the X values. These were the Y values. These do have to line up. Now remember, you are going to be responsible for learning how your specific calculator handles linear regression. If it's a scientific calculator or better, it should have built-in linear regression tools for you. I'm just using this online one, and it's going to go. And so we're going to get this linear regression equation. So let's interpret it. And I'll round to 3 decimal points. So let's see, 5.488. I'm just going to take a picture of it because it's not, my memory is trash. So back to this. Our equation was, if you remember, and I'm going to round to 3 decimal points, y, they use y hat, but I'm not super worried about that. Now let me pull up the picture I just took. 5.488x plus 50.967. That's our linear regression equation for this. Now for this data, X represented the number of hours a student studied for the exam. Y represented their score on the exam. What this says is that if we say, oh, what if a student studies 3 hours? We would plug 3 in for X, do all this business, and then whatever Y value that's spat out, we would say that's the prediction that this model makes for what grade they'd get on the exam. So if we want to predict the exam score, if a student studies 6 hours, we're going to plug 6 in for X. So we would do 5.488 times 6, add on 50.967. We get about 83.895, which we can round to about an 84. So we get that. Now, you can tell then, because the slope is 5.488, based on the previous interpretation of slope that we've made, for every 1 unit increase in x, we expect an increase in y of 5.488. And it's an increase because the slope is positive. So that's going to be our interpretation of slope here. So if the student would have studied about 2 more hours, she or he could have expected about 11 more points on the exam, or a 95. So I'm not going to worry about residual stuff. Interpreting the slope and the y-intercept, for each additional hour of study, the exam score increases or goes up by whatever that slope was, 5.488 points on average. It's just a prediction. It doesn't mean you're guaranteed to get more. It's just what this model predicts based on the data that's already been collected. Now, to interpret the y-intercept, you have to ask yourself, because the y-intercept is the y value the model spits out when the x value is 0. So is 0 a reasonable value for x? Well, is it reasonable that someone comes into an exam with no hours of studying? Yeah. And there are observations, if you go back up to the data set, there are observations, there are x values that hover near 0. Because one of the things we learn about these kinds of things is that a model is only reliable roughly in the original range of the data. So the model is only reliable roughly between 1 and 8 hours for x. If you try to do 22 hours for x, the model may not be reliable. It may not make sense. You can't do negative values for x. That doesn't make sense. But 0 is not too far away. In other words, we can safely interpret what the y-intercept really means here. So we'll say yes and yes to both of these questions. So remember, the y-intercept was 50.966, or excuse me, 50.967 was the y-intercept. We'll just round that to an even 51. So this was the y-intercept, And since we can make a fair prediction using the y-intercept because we answered these 2 questions, then we're going to say if a student were to study 0 hours, the model predicts that the student would make a 51 on the exam. That's what the y-intercept's interpretation is going to be here. If the slope had been negative, we would just say decreases here. Every increase in x leads to a decrease in y, at least the model predicts. Okay. Moving right along. So this is just what I was saying. You need to stay within the scope of the model. The x values you choose to predict with that you plug into the model need to be either within the range of the original x values or just a hair outside the range. So like I said, this data ranged from 1 hours to 8 hours. The x values ranged between 1 and 8. So you really shouldn't use 25 as an x value to make a prediction with. That's not going to make sense here. So another thing we could do as another example, we can basically make predictions about a person's systolic blood pressure based on their age. So this person is 70 and their blood pressure is 199. That's probably not good. I think you need to go to the hospital at that point. But this is just to kind of make a point here. So we're going to do a couple things. The first thing we're going to do, we're going to go and we're going to make a scatter plot. I got all kinds of plans for this one. So give me one moment. I'm going to go put all this data in. You can put it into your regression calculator. Boom, boom. I guess you're just what I needed. Okay. So we can make a scatter plot of this data. I'm going to do it using the Desmos graphing calculator. And the nice thing about Desmos is you can just type points in directly. We'll scale the data. All right, so let's share. Let me share what I'm doing with you. So what I've done, I've graphed a scatter plot of the data over here. And oops, 39 and 143. Let me just fix that point here. Okay, so we see scatter plot data. So along the x-axis, you're talking about a person's age. You're talking about a person's age here. And it looks like as you increase age, as you move across the x-axis to the right, the y values increase as well. So as someone gets older, their blood pressure tends to go up. That does seem reasonable. Now there's a couple other things we've done here. I calculated Pearson's R value, the correlation coefficient that we talked about last time, and it was 0.9199 or about 0.92. So that's a pretty strong case for linear correlation because it's close to +1 in this case. If it were close to -1, we'd still have a strong case for linear correlation. It's just it would be negative correlation. As one increases, the other tends to decrease. But here we have a positive R value. It's close to +1. So as one increases, the other tends to increase as well, which is exactly what we see. Now we can compute the linear equation or the regression equation here. 1.69424x plus 79.755. So what this is saying is that, well, the y-intercept we would normally interpret as what y value do you have for an x value of 0? But an x value of 0 doesn't make sense in this data, because look at the data, if you go back to it, and you'll see that a 0-year-old, a newborn baby, that is just not among the x data here. And it is pretty far outside the range. So the y-intercept is just not going to have a very good interpretation here. That's okay. It just means, no, it doesn't really make a whole lot of sense for us. But the rest of it can make sense. We still need the y-intercept. It's still going to tell us how to graph the line appropriately. It just by itself has no real interpretation. And then the slope says that, well, it's 1.694 roughly. It's positive. So for every 1 unit increase in x, we expect a 1.694 unit increase in y. In other words, every year you get older, this model predicts that you're going to see an increase in your blood pressure on average of 1.694. That's what that means here. And so, what was the y-intercept? It was 79.755. So there you go, bada bing, bada boom. There's a nice graph of the regression line there. You notice it doesn't cross through every single point. It gets close to crossing through this point. It might just do that, but the point could also be a little bit fat. And so it's really not technically on the line. This one kind of, it's close. This one's a little far away. This one's a little far away. But for the most part, this looks like the line that best approximates all those points, or gets as close to crossing through all of them as is humanly possible, which is exactly what the line of best fit is. So that's pretty cool. Everyone say cool. Cool. What we'll do is we'll find the equation of the regression line, check, already done, and we're going to use it to predict the systolic blood pressure of a 90-year-old man. Does it make sense to predict for a 90-year-old man? Well, the highest X value was 70. A 90-year-old man, that's kind of debatable. Let's just do it. Let's just do it. So, okay, so the linear regression equation was 1.69. I'll just round it to 3 decimal points. 1.694x plus 79, was it 79.755? I'm going to plug a 90 in for x. Multiply to the slope. Add on this 79.755. All right, I'm going to use my calculator. And that's something I can rarely say. This is one of the only classes where we allow a calculator for pretty much the entire semester. And if you've taken another math class here, you've probably noticed we don't allow calculators there. Now, I believe very strongly in actually not allowing calculators in general. In general. I'm a very strong proponent of, no, this is a math class. You're learning what the calculator is doing. That's the whole point of the math class. But in this statistics course, this just has a different philosophy, in my opinion, because some of the computations are just really annoyingly hard and mind-numbing pain in the butt, if we're being completely honest. And I'm not even all that interested in having you do calculations. I want you to interpret the things properly. Anywho, so 1.694 times 90 plus 79.755. So this model predicts a blood pressure of 232.215 or just 22. Well, that's dangerous. I don't think you'd be alive. That would tell me the machine reading is wrong. So maybe this model is not a great model. Maybe we just got a couple people in there who had ridiculously high blood pressure. Because all we did at the end of the day was we went and we got a sample of people, it looked like about 8 people there. We recorded their age and their blood pressure. We could have just happened by random chance, by sampling error, to have gotten a couple people who just have really high blood pressure. And so we generally, that's why we like larger samples. I'd rather have a sample of at least 100 if I'm doing a serious blood pressure study. And so you might have some people with high blood pressure, but then you have some with lower blood pressure, regular blood pressure, that's not so bad. And so that's going to skew the numbers away from us. But this model predicts a ridiculously large blood pressure for someone who's 90. And so now you can kind of see why maybe 90 was a little bit out of bounds for us. We tried it, we did it. We're going to ask for forgiveness instead of permission, but it maybe we probably shouldn't have done that. The model probably shouldn't have applied to a 90-year-old when the largest X value in the data was 70. But we tried it anyways, and we kind of see the result of doing that. So just interesting, but that is kind of an interesting idea. If this model was true, then your blood pressure goes up about 1.69 units every year you're alive. So that's a good warning sign to monitor your blood pressure. And dieting and exercising is also an important part of keeping your blood pressure regular. And I'm probably the last person who should be preaching that, because since COVID hit, I couldn't go to the gym anymore, and I loved going to the gym. Now I eat a lot of pizza and I don't work out, and I sit on my couch and I watch Netflix and stuff. So I'm usually the last person. If you can't use a regression equation, if you get an R value that is less than, you remember when we talked about this business here, we didn't go into uber detail about it. But if you get an R value that's too small and the linear regression equation doesn't make sense for that data, just use the average Y value. Just use Y bar, the average of the Y values. So for instance, over here, let's say this data actually produced an R value of like 0.3, which is just too small and linear regression doesn't make sense here. Well, then just take the average Y value, add up all these Y values, divide by, it looks like there's 8 of them. And whatever that is, you would predict that for any age. That's the best you can do there. Okay, so that about wraps it up for chapter 4. So we are rocking and rolling here at a pretty good clip. Real quick, I'm going to go ahead and just take attendance while I'm here. Mary Lee is here. Ryan is here in person. Tira is here in person. I see that Christian/Brooke Honeycutt is here virtually. I see that Kara is here, so I'm counting her present. I see that Viridiana is here. I also see that Samuel Collins is here. And anyone else? Brooklyn Patton is also with us. Hello, Brooklyn, you are here. All right. Very good. So then just one other quick announcement about the upcoming exam, other than that you're taking it on Canvas using Respondus Monitor. Also, we're not having class Wednesday, as per our regular policy of not holding class on exam days. So you can spend that time just, doing your exam on Wednesday. Okay, so we are now ready to kind of shift gears a little bit. And we're going to have to talk about probability. And it turns out probability is incredibly telling. Probability pretty much informs the whole rest of this class. It is necessary for a complete study of statistics. So let's see what's going on here. So we're now getting into chapter 5, but we just kind of have to for reasons that I have discussed already. So probability is a measure of the likelihood of a random phenomenon or chance behavior. Probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. That's a good definition for it. So basically, probability is our measure of how likely something is to happen. Either it's unlikely or it's very likely. Now, if you're a gambler, either at a casino or you do some sports betting, um, if you go into a game, and boy, who's the best team in the NFL right now? That's Kansas City. Yeah, that's probably right. All right, so Patrick Mahomes, you're a big Chiefs fan over there. Kansas City's probably the best team in the NFL. So imagine you were having Kansas City play one of the worst teams in the NFL, which clearly appears to be the Dallas Cowboys this season. So yeah, that sounds about right. If you've watched that game yesterday, they were doing fine early on, and then the defense just they started coming back at the end, but it was too little, too late. 500 yards from Dak Prescott was not enough. But if you had the Chiefs going against the Cowboys, the Chiefs should be completely favored in that game. What that means then is that if you were going to bet on the Chiefs, you're likely to win some money, aren't you? Yeah, if I go put $100 on the Chiefs to win, since I expect the Kansas City Chiefs to win, I expect that I'll get my 100 back plus whatever I earned in the gambling procedure, in the gambling process. But the thing is, well, then wouldn't you just always go bet on the best team? Well, no, because what they do is they don't just say, okay, if you bet $100 on Kansas City and they're very, very favored to win this game, you're gonna get $100 as a winnings. So you're gonna get $200 total back. No, they're not gonna do that for you. They're going to say, well, the Chiefs are going to win most likely. So if you bet 100 on this, we might only give you $20 in winnings. And then if the Chiefs end up losing somehow, you lose your $100. That's what that means. That's how they kind of balance it out for fairness. And now, since the Cowboys are not favored to win the game, if I went and bet $100 on the Cowboys, I might win $200 and get $300 total back coming back to me on the gambling website. Because they're not favored to win. So I should get more money and winnings than I bet because they're not likely to win. In fact, if you look at sports lines, you'll see like minus 190, minus 300, plus 270. Anyone that is minus means that they're favored to win. So even though that doesn't sound right because it's a negative number, but if the Chiefs are minus 300 on that game, that means you have to bet $300 just to win $100. And if they lose, you're out your $300, all 300 of it. The Cowboys might be plus 180 on that game. That means you have to bet $100 and you'll win 180 if the Cowboys do win. That's what those gambling lines mean. Now, I should not be maybe teaching you how gambling works, but whatever. You're all adults, and sports betting is now legal. So that's just how it is. But of course, don't gamble if you don't feel like gambling. But it's just so natural if we're talking about probability that we're going to bring up gambling. Okay, so I won't go into uber detail about the law of large numbers. This is also not technically, this is kind of a very basic understanding of the law of large numbers here. So what we're going to do is we're going to identify the different outcomes of we'll call it an experiment, the statistical process of having two children. So we're going to identify these things called events. So let me show you kind of how it works. We're going to have something called the sample space. The sample space is going to be a set. So if you've had set theory before, that means we use set brackets. And the sample space collects all the possible outcomes of a probability experiment. So here's what we're going to do. I'm going to list the 4 outcomes for the experiment of having 2 children, and we're going to be talking about the genders of the children. The genders of the children. And I'll use B for boy and G for girl. Here's the first possible event. You have 2 boys. So we're going to call that BB. That's our first event. You have two children. One of the possible outcomes is that they're both boys, BB. The next event we'll say is that you have a boy first and then a girl second. The next event is that you have a girl first and a boy second. And then the last event is that you have two girls. GG. Now, when I was coming up, GG meant got to go if you're using internet lingo from the AOL Instant Messenger. But nowadays, I don't know what, this is the TikTok generation. I don't know what GG means in TikTok speak. Now the sample space is going to be the set of all the possible outcomes, all gathered into one kind of thing. So I'm going to call it capital S. So in probability theory, we're going to reserve a capital S for a sample space. We have to use set brackets. And I'm going to list the four possible outcomes. The two boys, boy then a girl, and I have to use a comma to separate the different outcomes. Girl then boy, and finally two girls. So each of these kind of possible outcomes in and of itself by itself is sometimes called a simple event. It's just one of the possible outcomes. We're going to define more generally an event is any subset of the sample space. An event is any combination of any of these possible outcomes or even none of the outcomes, that nothing happens. So we're going to call the event E of having one boy. Let's look between the four outcomes, which of these go along with having one boy? Well, not this thing. This thing is having two boys. But here you have one boy. It's the first child you have. Here you also have one boy. It's the second child you have. So the event E then is BG, comma, GB. Now let me scroll down a little bit. Okay. That's what I thought. So just some simple definitions. Sample space, the set of all possible outcomes. An event is any combination of outcomes from the sample space. An event can have just one thing in it. That's called a simple event. An event could have had three things in it. Describe the event of not having two girls. Then that would be these first three things. An event can be all four things. An event can be none of them. We'd use the empty set in that case. So lots of things going on. Now, let's define some of the rules of probabilities. These are sometimes called Kolmogorov's axioms of probability. This is not all three axioms, but that's okay. So the first thing here, for any event E, we'll use this terminology to notate as the probability of E, P of E. It's kind of like a function like f of x. You're saying a function of x. Here you're saying the probability of the event E, the probability that this event occurs. It turns out that just logically speaking, let's think about the weather. Let's think about the weather. What is the lowest percent chance of rain you could have on a given day? 0. Yeah, it's not going to rain today, or it's not predicted to rain at all today. You're saying that's a 0% chance of rain. Can you have a negative 5% chance of rain? No, that doesn't make any sense, does it? It's nonsense. So a probability, the lowest you can go is 0 or 0%. It doesn't make sense to go lower than that. It can be 0. It just can't go beneath that. What's the highest percent chance of rain you could get? 100%. Yeah. Does 110% chance of rain make any sense? No. And when someone says, I'm going to give 110%, that's just a kind of a rhetorical strategy. They're saying, I'm going to give a lot, all my effort, and then some. But you can't literally give 110% effort. It's just kind of like an old joke you say. So the highest chance of rain you could get is 100%. Well, chance of rain, all that is the probability of rain, or what someone predicts to be the probability of rain. So the highest you can go is 100%, but when we deal with probabilities, we actually write them in decimal form. So 1 is what 100% is written and it's as a standard decimal number. So you could tell yourself this is 0% up to 100%. But really we say 0 and 1. And it's because when you're actually doing math, the math behind it, remember you got to convert your percent to a decimal first. If you want to take 25% of something, you convert 25% to the decimal 0.25, and then you multiply it. We also have another very interesting rule, and it says that if I were to add up all the probabilities in the sample space, in other words, if I take every possible outcome, if I take its probability and I add them all up, then it must add to 1 or 100%. Which again makes perfect sense. The highest you can go is 100%. You can't say, all right, the probability that the Cowboys win plus the probability that the Chiefs win is 300%. That doesn't make any sense. The probability that the Chiefs win might be 90%. That automatically forces the probability that the Cowboys win to be only 10%, so that you add them together and you get 100%, which is 1, just the number 1 as a decimal. Nothing else makes sense. So that's all this rule is saying. You can't add up all the probabilities and get 1.5. That doesn't make sense. So now we can talk about something called a probability model. I did some probability modeling when I was a younger guy. I did modeling in various math magazines. I don't have, this joke isn't going anywhere. This is just a dumb joke. I know I never did any modeling. Why? I don't know. You know, I probably should have done some modeling. Math modeling. Anyways, I apologize for that joke. It wasn't funny. Please disregard the previous joke. A probability model. Man, my jokes have gone off. They've gone downhill. And I'm just going to blame COVID because it's easy to just blame COVID. And I'm going to say, well, I've been quarantined. My social interactions have gone down, you know, since March. That's just what I'm going to say. I swear I used to be funny, guys, please. Or maybe I was just always deluding myself. So all a probability model is going to be is just basically it lists the possible outcomes of a probability experiment and each outcome's probability. It's just something that tells you how the probability for a specific scenario ought to work or how it's going to work. So let's say you had a bag of 100 peanut M&M candies. Now, you might have to get the what do they call it, the share size, or maybe you have 2 share size bags that you're putting together, and you have 100 total peanut M&Ms. If 12 of your M&Ms are brown, 15 of your M&Ms are yellow, 12 of your M&Ms are red, 23 are blue, 23 are orange, and 15 are green. Let's say that is just, you counted them out for some reason. Then let's say you were to put all those M&Ms back together in a jar or something, close your eyes, shake the jar up nice and vigorously, and go pull one out at random with your eyes closed. If there were 12 out of 100 of your M&Ms were brown, then you can argue there should be a 0.12 or 12% chance of pulling a brown M&M, right? And yeah, that's exactly right. There's only 12 out of 100, so there's a 12 over 100 or 12% or 0.12 probability that that one M&M is going to be brown. Thus, this, as long as all these probabilities add up to exactly 1, this is going to be a probability model. So let's verify that that works. Let's see. I need to add them all up. it needs to come out to 1/100%. So let's see, let's do it. You can use your calculator, but I'm going to try to do it in my head. 0.12 plus 0.15, 0.27 plus 0.12 again, 0.39 plus 0.23 is going to, well, what's 39 plus 23? It's going to be, I don't want to do this, 40, 50 something. Anyways, plus another 0.23 plus 0.15. Yeah, that does add up to 1. And did I actually do the math in my head? No, I got lazy and I just said it does. But you can verify it. It does. I've worked this example before. You can verify it and you can see that, oh yeah, all the probabilities add up to 1. If for some reason I accidentally left green out of here, I just made a goof or I intentionally left it out of there, and I only added up these ones, that would only add up to 0.85, which is not 1. So that this, just without the green, these would not be a true probability model because the model has to follow the rules and the laws of probability. There's no getting around that. So there you go. This is a probability model. It just tells us how certain events or certain things ought to behave in a probability standpoint. You can tell right here, this is not going to be a probability model one bit. Even if I were to add all of them up, if I added all of them up and it came out to 1, no. This is a negative number here. This is a negative probability for getting a brown M&M. No, that's not possible. Negative probabilities don't make sense. You can have a 0 probability. That just means something is impossible. You can have a 0 probability, but you can't be any less possible than impossible. And impossible has a probability of 0. Now, if you had another color, purple, there were purple M&Ms. I don't know if there are, but if there were purple M&Ms, but there did happen to be no purple M&Ms in the bag, you wouldn't even include it here, but you could say the probability of getting a purple M&M is 0 because there aren't any. It's not on this table. But this is not a true probability model because of a negative probability. It doesn't make sense. Here, all the probabilities are positive numbers, which is good, but add them all up. When I'll do that now, I'll just use a calculator. You get 1.14. No, that's not a probability model because they all have to add up and come out to exactly 1. Now, if for some reason, if I did these calculations and this came out to like 0.222222, and this was like 0.2568794, blah, 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 if the numbers got a little bit nasty and you had to round the numbers, then when you add them all up, it may not come out to exactly 1, but secretly it is. You just had to round, and that slightly screws the numbers up just a tad. But in truth, it would have added up to 1 if you didn't ever round. So just keep that in mind. You might come out to like 0.997, but you have to just know from yourself that it was just rounding error that caused it. So neither of these are probability models. And so, if an event is impossible, the probability of that event is 0. If it's impossible, it ain't going to happen. It has a 0 probability. Conversely, if something is guaranteed to happen, the probability of that is 1 or 100%. Your professor, Joshua Gunther, is guaranteed to win a Super Bowl someday. Even though he's 31, has never played any real football in his life, he's somehow going to win a Super Bowl. No, that would actually be impossible. So that's going to have a probability of 0. I mean, it's just not going to happen that I'll win one as a player. It's just not going to happen. I've given up on that dream. And I just play Minecraft instead, like I said. If event is guaranteed to happen, it's got a probability of 1. And then what we'll do is we'll call an event unusual if it has a low probability of occurring. It's still possible. It could rain frogs today. If you've ever seen the movie Magnolia, it could rain frogs. Or on my drive home, I could run into snow. I don't know. It's theoretically possible, It's just very low chance of happening. What we're usually going to do is we're even going to say generally less than a 0.05 probability or 5%. That's usually the definition of unusual. Of course, who cares what, it's just some word they're using here. But that's what your textbook likes to call it. If it's less than 0.05 or a 5% chance of happening, we'll call it unusual. So yeah, just some basic definitions kind of to start off chapter 5. Oh, that's a little bit frightening. Pass the pigs game. So the empirical approach, there's actually going to be 3 different forms of probability. We call them the 3 types of probability. The first type we're going to look at is something called empirical probability. This is where we run an experiment. We repeat the experiment multiple times, and we measure how often an event occurred and divide it by the total number of times we ran the experiment. And that's how we're going to calculate the empirical probability of that event. The word empirical simply means something which is observed, which has occurred, is a past event after the fact, but we've observed it and we've observed it well. We've taken good notes, or we've, whatever, however you want to call it, we've actually done a little bit of objective looking at it. So empirical probability. So for instance, if I flip a quarter, you generally would say there's a 50-50 chance of getting heads. But if I flip the quarter 100 times, it is possible that I could get 57 heads, right? Yeah, it's possible you get exactly 57 heads and thus 43 tails. So in that particular scenario, you might say the empirical probability of getting heads based on this experiment I just ran is 57% or 0.57. And that's accurate. That is the empirical probability. You'll quickly see, though, the empirical probability may not fully satisfy kind of our what we feel probability ought to be, because we know that coin normally would give me heads half the time. So what I just said, by saying that heads should be a 50% chance of happening, what I really said was that was under like perfect scenario or perfect conditions. Also, that doesn't mean it's guaranteed to happen exactly half the time in practice. It's just what it ought to be. So there was a game called Pass the Pigs. I don't know if you ever played it. You know, it might be in like your closet somewhere. But there was a Pass the Pigs game where pigs are used as dice. That's kind of cute. Points are earned based on the way the pig lands. There are 6 possible outcomes when a pig is tossed. A class of 52 students rolled these pigs 3,939 times. The number of times each outcome occurred is recorded on the table to the right. So instead of rolling a standard 6-sided die where you have 1, 2, 3, 4, 5, 6, we are rolling some pigs, which is pretty cute, I think. I don't know. When I was younger, I used to be a lot more cynical about things, like cute. Huh, there's wars going on in the world, or, you know, something like that. And now I'm like, no, that's pretty cute, whatever. So of the 3,939 times the pig was tossed, it landed on the side with no dot 1,344 times. It landed on the side with the dot 1,294 times. It landed on the razorback side 767 times, and so on. Thus, we can compute the empirical probability of that each of those things happen. Empirically speaking, it'll land on the side with the dot by taking 1,344 and dividing it by the 3,939 times it happened. We're just taking a ratio of how often something happened compared to how much was actually went into it, or how many total times we ran the experiment. So I'm going to use my calculator, as we will need to. We'll round to 3 decimal points, and we'll fill out some of this probability table. So the side with no dot, that happened 1,344 times out of 3,939 times. And so if we take that and we round to 3 decimals, we get about 0.341. So a little more than 34% of the times that we rolled the dice, we observed the side with no dot. And so we would go down the list there and we would compute the probabilities kind of for all of them, side with dot. It reminds me a lot of a frequency distribution. In fact, that's exactly what it is. Remember, we computed frequency distribution diagrams and we drew histograms of them. And so we would just do that for all of the different values here. And what we should see is that if we were to add up those probabilities, it may not come out to 1 exactly because we rounded, but in theory, it would come out to 1. Now, what we really are interested in is the classical method. This is also known as theoretical probability. Oh. Theoretical probability is actually a better term for it. And the way this works, the major difference between classical probability and classical/theoretical probability and the empirical probability method we just discussed, where we actually went out and ran an experiment. Empirical probability is based on observations of events that have occurred. And specifically where we actually take notes and we write down exactly what happened. But it's based on past events, even if they're very, very recent. We just did it 5 seconds ago. It's still technically a past event. That's also known as a posteriori, if you like fancy terms. The classical method, it computes probabilities based on how it ought to happen. We take a probability experiment and we say the number of ways our specific event can occur, and we divide by the number of possible outcomes. And that's how we compute the probability of our specific event. This also, well, no, never mind. I won't go any further. So for instance, if I flip a coin, there's 2 possible outcomes, heads or tail. So 2 would be the bottom number. That's the number of possible outcomes. Now, the number of ways I can get the outcome I want, which is a heads, is only 1 way. So we're going to say there's a 1/2 probability or a 50% or a 0.5 probability of getting a heads. If you roll a dice, if you roll a standard 6-sided dice and not a pig, if you roll a standard 6-sided dice, there's going to be 6 possible outcomes. There's going to be 6 possible outcomes. If you want to know the probability that you get a 2 or greater on the dice, a 2 or greater on the dice, well, you got a 1, 2, 3, 4, 5, 6 on the dice. So count up the number of outcomes that are 2 or greater. 2, 3, 4, 5, 6. I counted 5 total outcomes. Does that sound about right? So if I roll a standard 6-sided die, 5 of the outcomes go the way I want out of 6 of the possible outcomes. And so that gives me about a 0.833 probability. The 3s actually go on forever and ever. Or about an 83.3% chance that things are going to go the way I want and I get a 2 or greater on the dice. There might be some kind of casino game you're playing where you need to get a 2 or greater on the dice. Okay, I think that's a good stopping point. So remember, your exam is this week. You need to take it by Wednesday evening at 11:55 p.m. We're not going to have class on Wednesday. The exam is in Canvas using the Respondus Monitor system. You have your Exam 2 formula sheet in there. You have an Exam 2 review that you can access on MyLabs Plus. You can always go back in on MyLabs Plus using the gradebook in MyLabs and work old homework assignments that are now past due and get more practice. You won't change your grade, but you will get more practice for them. So that's another thing you can study if you want some more studying outside of just the Exam 2 review. Other than that, y'all have a great day, and I won't see you Wednesday, but I'll see you next Monday for class.